neuroscience. I've done a lot of work on mechanisms, mechanistic modeling, and a lot of work in empirical neuroscience as well as in theoretical. And talk to us about Bayesian modeling, unification, and constraints.
Thank you, Richard, and thank you for the invitation to come speak to you. Thanks for everyone for coming. So it's a real honor to follow up after, so it's an honor and also a challenge to follow up after Andy. His work has been inspiring me since I read Being There some time ago, and sort of ongoing influence of his work is really pronounced in my own sort of thinking about philosophy and cognitive science. So it's really a great sort of privilege to follow up. But I guess a bit daunting. Okay, so I was also sort of taking the idea of a workshop quite seriously, and some of this is a work in progress, and so there are many people in the room who are experts on some of the issues that I'll touch on today. Your feedback would be really, really useful to me, so I welcome the opportunity for feedback at the end. I also just wanted to mention that a lot of this work has been done in collaboration with my PhD student Chris Hewitson, who's somewhere around. So I just wanted to mention him now. Okay, so let's get going. So what I want to do today is just very briefly sort of talk about the sort of what Bayesian modeling is in neuroscience and cognitive science. For this audience, I don't think I have to belabor the details. And then I wanted to sort of talk a little bit about unification. Actually, some of the things that I'll say I think dovetail quite nicely with some of the things that Andy said in his talk about unifying, the sort of unifying power probabilistic approaches in general. So hopefully some of the things I say, even though they are specifically sort of addressing Bayesian sort of modeling in cognitive science, I think have more general import into sort of issues about probabilistic approaches in general, and I think also predictive coding, predictive processing approaches in particular. So it'd be interesting to sort of think through some of those issues possibly. So I'm going to focus in on Colombo and Hartmann, sort of some of the issues that they raised. Actually, it says 2017, but this is actually the same paper that Andy referenced, 2015. It just came out in print, and so I just used the page numbers from the in-print version, so if you're confused, there's not a new paper, it's the same 2015 paper, it's just the page numbers are referencing the print version. Raise a couple challenges, and then at the end I'll sort of sketch basically what I see is one way of kind of moving forward with this some of the issues that I raised in terms of providing a kind of explicit theory of constraints and sort of what's operating when we're building models and thinking about the data that we use as evidence as evidence for our models. Okay, so Bayes' rule. Oh, nice. All my lines are going to be cut off, and I have the brilliant design of the lines in the monitors here. So Bayes' rule. This is fundamental sort of model that we've got for characterizing statistical inference, has to do with updating our beliefs or updating information, sensory evidence based on the current sensory evidence and also some history some information from the past. So just to walk through it very quickly, you've got the posterior on the left-hand side, the posterior probability distribution, which is the probability of the hypothesis given the data, and that equals or is proportional to the probability of the data given the hypothesis, the likelihood function, times the probability of the hypothesis, the prior, and then normalized by the probability of the data. So the probability summing to 1. So that's the sort of idea. This has been applied very widely across many different cognitive domains, many of which Andy talked about in his talk. Sensory motor learning, multisensory integration, just to name a couple very prominent ways in which Bayes has been applied: perception, vision, audition. So as I said, it's also been an approach that's been sort of very heavily used. Perhaps the sort of paradigmatic examples of application of Bayesian modeling approaches in neuroscience have been to sort of think about how this formalism is usefully applied to characterize how two different kinds of sensory information might be integrated, where the integration, the different types of cues are weighted as a function of their reliability. So here is just basically the same sort of the same Bayes rule, just with different variables, where you now you're characterizing some parameter of interest x, given two different types of cues. So it could be vision and it could be cues from vision and audition. It could be cues from the case that I'll talk about in a little bit is integration of vestibular cues about motion, heading direction, and visual cues about heading direction. So basically, the posterior probability distribution of this parameter of interest, say heading direction, is given visual cues and vestibular cues equals the probability of the visual cues given the parameter of interest times the probability of the vestibular cues given the parameter of interest times the prior. So basically now we're not talking about multiplying just a prior and the likelihood. We're talking about multiplying two likelihoods. Okay. Excuse me. So I think it's just sort of worth mentioning some of the things that I'll be saying, sort of touching on some issues, I think, more general issues in philosophy and science. So I thought it was worth sort of drawing a distinction, and this is a bit clumsy, I'll admit, but I think that it's important to distinguish between what I'm going to just call Bayesian modeling versus Bayesian computation. And I think this is very analogous to the distinction that others have drawn in the literature between computable and computational on the one hand, or maybe computational modeling and explanation on the other. So different people have said it in different ways. And actually, Timothy Van Gelder, in that sort of famous PBS article, actually draws the same kind of distinction, talking about the computational approach to cognition. And so the idea is to a first approximation, this is Walter Piccinini's characterization, to a first approximation, the distinction we need is that between using a computational description to model the behavior of the system and using it to explain the behavior of the system, such as when computer scientists explain what computers do by appealing to the programs they execute. By contrast, in computational modeling, the outputs of a computing system C are used to describe some behavior or another system S under some conditions. The explanation for S's behavior has to do with S's properties, not with the computation performed by the model. And so basically what you're getting at is whether the computation is actually being used or implemented by the system, the target system that we're interested in, or whether we're using computers to model the phenomenon. And I think the same sort of distinction applies in the context of Bayesian modeling. And so the sort of upshot of this is that the widespread success of, I should actually mention, with the Bayesian formalism, you don't have just the Bayes rule alone, you don't have all the machinery, theoretical machinery you need in order to say, use as the basis for an action or decision. You also need to characterize some kind of loss function that allows you to basically select, could be the mean of the posterior, that allows you to select one value from the posterior distribution that's the result of applying Bayes rule. So that's when I say Bayesian decision theory, that is both Bayes rule and also some of the characterization of this loss function. So the widespread success of Bayesian decision theory as a modeling framework for behavioral and neural data across a wide range of domains, including perception, sensory, multisensory integration, and sensory motor learning, doesn't provide evidence that the brain performs Bayesian computation. And really what we're interested in is something that Neil and Peugeot described quite a long time ago. They talked about the Bayesian coding hypothesis. Essentially the hypothesis that the brain represents probability distributions and performs probabilistic inference or approximate probabilistic inference. And we could probably debate for the rest of the time what it means to represent a probability distribution, and sort of encourage you to sort of, we can talk about that in the Q&A perhaps, But that's the sort of idea that I think really sort of drives neuroscientists to sort of try to address these. And I think this is exactly sort of the way that Andy has been talking about the power of predictive processing framework. It's because the brain actually implements predictive processing, not just so we can use these models that have this certain kind of hierarchical Bayesian structure in order to accommodate various data sets. So it's, I think, an obvious point, but I think an important one to mention. And so here's just one characterization. I don't think this is truth by any stretch, but I think this is sort of just a very sort of exemplary kind of characterization of how neuroscientists tend to think about the state of play in contemporary neuroscience with respect to the Bayesian coding hypothesis. So this is Peugeot and review article. There is strong behavioral and physiological evidence that the brain both represents probability distributions and performs probabilistic inference. And so really what I want to do today is to sort of raise a couple challenges with sort of how we move between different kinds of data sets, behavioral, neural, and then try to draw inferences or try to take that data as or the appropriateness of a Bayesian model for those data sets as evidence that the brain actually implements something like Bayesian computation. Okay, so now I want to talk a bit about this sort of connection between unification and explanation. And again, this is something that Andy mentioned. It's often heralded that one of the sort of alluring properties of these kinds of modeling frameworks, the Bayesian framework specifically, or more generally probabilistic approaches, is that they sort of have this deep unifying power. They're sort of bringing together a lot of seemingly disparate phenomena under one common formalism. And in virtue of that, some conclude that this endows this framework with explanatory power. So I just wanted to address that. So here's just a couple quotes from the literature. There are many, many more that one could select. Here's Griffiths et al. Saying, probabilistic models provide a unifying framework for explaining the inferences that people make in different settings. Bayesian decision theory offers a unifying mathematical language for framing cognition as the solution to predictive problems. One particularly appealing aspect of these theories is their generality. They can be used to model a wide range of tasks, from sensory processing to high-level cognition. Most, if not all, of the computations performed by the brain can be formalized as instances of probabilistic inference. Sensory processing, motor control, decision-making, learning, and virtually all higher cognitive tasks fall into this class. By treating them as probabilistic inference problems, we may be able to derive general principles that apply to all of these areas. Right? So it's quite a grand claim. And there are others that have sort of also said similar things. So this is more particularly applied to predictive coding. So for what it is really, I was trying to furiously scribble down, I think Andy had a quote that was very similar to this in his talk. And I don't think he's committed to some of the claims that I'm going to be, a particularly strong view about the link between unification and explanation. But I think there is this sort of this allure in appealing to the unifying nature of these principles. So for what is really on offer, so it seems to me, is best seen as a framework whose primary virtue is to display some deep unifying principles covering perception, action, and learning. Action-oriented predictive processing models come tantalizingly close to overcoming some of the major obstacles blocking previous attempts to ground the unified science of the mind, brain, and action. And then just this first thing, the free energy principle is an attempt to explain the raw structure and function of the brain. Right? So the scope here is really wide. So I guess one worry is that there's a sort of kind of recurrent sort of, to the extent that there's sort of an attempt to draw a link between unification, the unifying power of this formalism, and its explanatory power, it's sort of reminiscent of another recent debate in the philosophy of cognitive science, one that I was involved in just a couple of years ago. So this is Stepp and Chimero and Turvey, saying that dynamical explanations do not propose a causal mechanism that is shown to produce the phenomenon in question. Rather, they show that the change over time in a set of magnitudes in the world can be captured by a set of differential equations. Some dynamical models act as guides to discovery. Indeed, in the best dynamical explanations, an initial model of some phenomena is reused in slightly altered form so that apparently divergent phenomena are brought under a small group of closely related models. Thus, dynamical explanation can provide unification in the sense discussed by Friedman, which are these sort of famous articulations of the unificationist account of explanation. The best dynamical models can be used to unify disparate phenomena, capturing them under a single explanatory scheme. Similar claims about the explanatory import of I'm going to call mathematical unification under a common mathematical framework, have been made about canonical neural computation, network analysis, and a number of others. So I guess there is a sort of worry that we potentially, in trying to bind those two too closely together, we're making some of the same mistakes that we made in the past. And I think so it's important to sort of recognize that there have been responses to that sort of attempt to defend a unificationist sort of view of explanation. I think that many causal approaches to explanation and mechanistic approaches to explanation sort of don't prioritize unification as a real important sort of property of explanatory models or generalizations. So here's Chris Hitchcock and Jim Woodward. It's an early paper that's sort of articulating an interventionist account of causal explanation where they're talking about scope of generalizations. And they say that increased scope does not always correspond to explanations that are intuitively deeper. And so they give this nice example of a neural circuit that's found in this one particular kind of snail. N1 is this neural circuit that's highly conserved across a diversity of species. So you get this really wide scope for the generalizations or the models that characterize that neural circuit. And then you've got another situation where you've got a highly specialized neural circuit that maybe only exists in this one particular species of snail. So it's really sort of scope limited. Its scope is basically it covers this one particular species of snail. And they want to say that while the unification account seems to yield the conclusion that the generalizations governing N1 provide more unified and hence better or deeper explanations than the generalizations governing N2, simply in virtue of applying to more organisms or more different kinds of organisms, our account avoids this unintuitive conclusion. So according to the interventionist approach, unification or wide scope or generality, I'm not saying they're all identical, but they're all interrelated notions, is not necessary for causal explanation, and they go on to provide an account that's perhaps well known to many of you, where it's more about the range of invariant relationships that hold across interventions. And really the same kind of thing sort of is said by mechanists. I'm not going to go through the details, but the mechanistic approach to explanation basically sort of is aligned with the interventionist or many causal approaches in that scope isn't unnecessary, or wide scope is not a necessary property of explanatory models. And so here's just a sort of way, I think a useful framework for thinking about the different dimensions of variation for mechanistic models. And this is coming from Prager and Darden's book in 2013. And this is really just a sort of snapshot of a view that's been developed in many places over many years. So they talk about completeness, which is sort of movement along this dimension from a sketch of a mechanism to a schema. So you've got basically a mechanism sketch, which is incomplete or partial representation of a mechanism that has gaps. So it's only some of the parts, activities, and features of the mechanism are actually characterized in the model. Just another, the other end, which is a mechanism schema, which is a representation of the mechanism that's complete enough for the purposes of hand. But then maybe some of the details are abstracted away from because they're not relevant to the particular model. Then you've got detail. I'm just kind of breezing through these because these aren't the ones that are so relevant. But you've got detail, which is abstraction, so the process of dropping details, and specification, which is the process of adding details. And then you come to evidential support. So this is a dimension moving from how possibly a model, so how does it possibly work, to a model that we might describe as being how does it actually work. So how possibly models are sort of loosely constrained conjectures about how the mechanism works, how plausibly models are consistent with more or fewer known constraints on the components of the mechanism, and how actually are heavily constrained descriptions of the real components, activities, and organizational features of the mechanism. So we can quibble with some of the details, but I think the general idea is that there's this kind of this continuum of evidential support. And then you get to generality or scope, moving from narrow to wide, which is just the size of the domain to which the model applies. So we can think about those domains in terms of species. We can also think about them in terms of cognitive domains, like perception, multisensory integration, decision making. That's the kind of thing that I'm thinking is more relevant for the examples here today. But importantly, not all of these dimensions bear equal weight for a mechanistic explanation. So complete and support are really, really important. Mechanistic model is explanatory to the extent that it completely and accurately describes the relevant parts, activities, and organization underlying some phenomena. So there's really sort of an important kind of caveat here. It's all about sort of relevant details, and that's relevant to the phenomena to be explained. And it's not exhaustive completeness. It's not that we just want details for the sake of details. And then generality or scope is also relatively unimportant. So completeness and then that really falls out of the fact that completeness and support can be satisfied equally well by models of single cases, or sort of say a limit n of one systems. There's only one system to which the generalization of the model applies. They can satisfy completeness and support as well as a model that has wide scope. So a model for highly conserved biological mechanisms, like say the Hodgkin-Huxley model of the action potential. So I think in terms of a kind of motto, I think reasonably sort of decent way of characterizing this idea is that explaining more things doesn't necessarily equal more explanatory. It doesn't make the model more explanatory. And this really is in contrast with unificationist approaches, where what it is to be a good explanation is deeply tied to its ability to unify a diverse range of phenomena. And again, I just sort of draw that this is not exclusive to the mechanistic approach to explanation. This is parallel in other causal approaches to explanation, including the interventionist approach. Okay. And so I think that, and there's also just one other point, is that, so that's sort of about why unification isn't necessary for explanation, but it's also not sufficient. And so Margaret Morrison, probably more than anyone else, has offered an account of unification that shows how heterogeneous that concept is. So there's many different kinds of scientific achievement that are captured by this idea of unification. Not all of them we would want to count as explanatory achievements. So descriptive unification, where we posit some common descriptive or classificatory scheme with really being explicit about having no explanatory objectives, like Linnaean taxonomy. And similarly for, I think a sort of subset of that would be a kind of quantitative descriptive unification, where you've got a common mathematical framework for formalism which can be applied to many different sorts of phenomena. So the fact that we can construct a common mathematical framework for dealing with a range of different phenomena doesn't guarantee that we've identified some common causal or mechanistic factors responsible for those phenomena. And that would be something like physical unification, which is bringing them together by appealing to some common set of causal relationships or mechanisms. And that, I think, many would want to sort of assert has a much closer tie to explanation. So I don't have a thought on it. Okay, so now I'm going to go and address a couple of the claims made by Colombo and Hartmann. So that's really, I think, just to sort of set the stage for thinking about Bayesian modeling frameworks, their connection to explanation, and how I think it is not the right way of thinking about their explanatory power in terms of their unifying power. At least not. And Colombo and Hartmann actually agree with me on this. So this is not the place that I think is, this is not where there's daylight between the views. So in an earlier paper, Colombo with neuroscientist Peggy Series said Bayesian models do not provide mechanistic explanations currently. Instead, they are predictive instruments. So I think this is sort of shedding some light on where I think their account was going in the 2015 paper. That's why I bring it in here. And so in the 2015-2017 paper, they say, in sum, unification in Bayesian cognitive science is most plausibly understood as the product of the mathematics of Bayesian decision theory, rather than a causal hypothesis concerning how different phenomena are brought about by a single kind of mechanism. And so I agree with that. Rather than addressing the issue of the conditions under which a model is explanatory, we accept that a crucial feature of many adequate explanations in cognitive sciences is that they reveal aspects of the causal structure of the mechanism that produces the phenomenon to be explained. In light of this plausible claim, we ask a question that we consider to be more fruitful. What sorts of constraints can Bayesian unification place on causal mechanical explanation in cognitive science? So I actually think this is a move in the right direction. It's sort of not tying sort of the account to sort of a link between unification and explanation, but sort of thinking about what other uses could this sort of unifying mathematical framework provide? They provide constraints on models that we deem to be explanatory. And so they identify three different types of constraints: constraints on mechanism discovery, constraints on the identification of causal and mechanistically relevant factors, and constraints on the confirmation and selection of competing mechanistic models. I'm just going to focus on, primarily I'm going to focus on the first one, and I'm going to circle back to the third one at the end. Actually, the first two are very closely related, and sometimes it's hard to sort of see how those stuff collapse into one another, but I'm not going to address that any further here. Okay, so really what they say about these constraints that Bayesian unification can provide for causal mechanical explanation is to say that it can provide a very useful discovery heuristic. So basically, neuroscience and cognitive science sort of starts by assuming some mapping between elements in a behaviorally confirmed model and then a neural model, which basically places useful constraints on the search for possible mechanisms. Now here's what they say. The basic idea is to establish a mapping between psychophysics and neurophysiology that can serve as a starting point for investigating how activity in specific populations of neurons can account for the behavior observed in certain tasks. Typically, the mapping is established by using two different parameterizations of the same type of Bayesian model. And they go on to say, drawing on this mapping, one prediction is that neural perceptual weights will exhibit the same type of dependence on Q reliability. Essentially, you've got two parameterizations of the same Bayesian model that I put up on the screen at the beginning of the talk. And there's a really nice mapping relationship, clear mapping relationship between the two. And then they say, more concretely, fetch et al. Provide an illustration of how Bayesian unification can constrain the search for space for mechanisms, demonstrating one way in which a mapping can be established between psychophysics and neurophysiology. So that's the sort of idea. Now, I'm not going to go through all the details here. I'm happy to sort of come back to them in the Q&A if people have them. But really, the basic idea. So this is this fetch et al. Study that Colombo and Hartmann spent a good deal of time talking about in their paper. And it's basically an experiment where they train monkeys to perform a heading discrimination task. And so, is this working? I think that's not working. Do we have it there? What's that? Yeah, that looks good. That works. Okay, so up here you kind of just see a really a cartoon depiction of the setup. So you they basically have this really nice way of independently manipulating the reliability of the vestibular cues by rotating this platform that the monkey is performing the task on. And then also they use moving dot stimuli to indicate the motion of visual motion, the direction of visual motion. And that's a really nice stimulus to use because you can actually sort of quantitatively change the level of coherence in the motion signal. So in this particular experiment, they used visual stimulus that was either moving all the little dots, which are really hard to see here, I apologize for that, where 16% of the dots are moving coherently, either in the rightward direction or the leftward direction, or 60% of the dots were moving coherently in the rightward or the leftward direction. Okay, so it's a really nice manipulation that allows them to then test how is the change in reliability of that visual signal, how is that reflected in behavior and in neural activity? Or is it reflected in behavior or neural activity? So the first step was to establish that it is in fact reflected in behavior. So basically what they do is they use single cue conditions to establish the behavioral thresholds for the different cues, so for the visual cue or the vestibular cue. Vestibular cues that indicate a particular direction, so from 0 to 10 to the right and to the left, -10. And, and basically the vestibular cue is, they don't manipulate the reliability of that cue. So that's always vertical. The only one they're manipulating is the reliability of the visual motion cue. And what you can basically see is that, so this is the psychometric curve, and here's the sort of, what you can imagine as kind of the baseline, the vestibular signal in the single cue condition. And what you see is a shift, a lateral shift in the psychometric function for the high visual coherent condition. And then what you can see here is that when you run so these are sort of now C and D here is plotting the combined condition, where the monkey is receiving both a vestibular cue and a visual motion cue. And then asking how is that being integrated and then reflected in behavior. And basically what you can see here is that, so the coding here is +4 is where the visual motion signal is to the right and the vestibular signal is to the left. And then -4 is the reverse. And so what you can see here is that for the low coherence, you get a shift in the proportion of rightward choices. So the proportion of choices in which the monkey sort of saccades to the right. Sorry, I should have said that. That's how they report the precision. We can't ask them. So they ask them by having them saccade either to the left or the right. And so that's what's being plotted over here. And what you can see is that in the low coherence condition, where there's only 16% of the dots are indicating motion to the right, you can see that the vestibular cue the vestibular signal is being prioritized. And over here in this plot, what's being prioritized in the high coherent, now we're in a situation where there's a high coherent visual signal, so 60% of the dots are moving in the rightward direction. And what you can see is that the psychometric curve shifts to the left, indicating that it's using the more reliable signal over the vestibular signal. So it's upweighting that. Now, once they established that there was a behavioral effect of this manipulation, they went on to sort of record single unit activity in neurons in area MSTD, which is a motion sensitive area that's known for many, many years to be responsive to visual motion. And what you can see here in A is basically the responses of an example neuron, so a neuron that's representative of the broader population of neurons that they recorded from in MSTD. And what you can see is that for this particular example neuron, it basically has a preference for visual motion to the left. That's what this is showing. So you can see that the slope is, so when the visual motion is to the left at -10, this particular neuron elicits a large response, and when its visual motion is to the right, it issues a much smaller response, and there's sort of intermediate values in between. So these are just tuning curves. And so what you can see is for the high coherence condition, there's quite a strong response. is it's responsive to visual motion. But there's also tuning of the vestibular only in the vestibular only condition. And then there's a small but detectable tuning curve in the low visual coherence condition. So you can see that there's still a tiny bit of a slope from left to right. So basically all this is establishing is what's the preferred tuning of this particular cell. And it cares about leftward visual motion. And then in the combined condition is really where they can start to assess the extent to which changing motion coherence, so changing how strong that visual motion signal influences the firing rates of the cell. And so what you can see here, again, plus, this means the blue is delta -4, which again means that the vestibular signal is to the left and the visual signal is to the right. And what you can see is there's not much of a difference here. But there is a small elevation in firing. Sorry, I'm messing up the details of that particular plot. Let me go to C quickly. So C, you're seeing the high visual coherence condition. And what we're seeing is when the visual signal is, the green trace is showing when the visual signal is to the left. Sorry about that. It's flipped around in my head for a second. The coding is so complicated in terms of -4 and +1. So what you're seeing in this plot here is when the visual signal is highly coherent, you see a stronger response, an upgrading of the response for the visual signal. And here's just the sort of model fits for these data. This is for the population data. I'm not going to go through the details because we're going to run out of time. But basically what you can see is these are sort of the R-squared, so the correlations for the model fits to the neural data. And basically it fits for both the low coherent visual condition and the high coherence condition. So that's sort of these two plots here, A and B. And then here what you can see, this is really where this is the main take-home message, is that the modeled neural weights for sort of weights that are sort of reliability, dependent on the reliability of the visual signal, change as a function of whether the coherence, if the coherence is high, then the modeled neural weight for the visual cue is higher than for the low coherence. And the reverse pattern is true for the vestibular neural weights. So there the weights for the vestibular cue are higher in the low coherence condition. So basically you get this sort of shifting patterns of these reliability dependent weights as a function of the reliability of the visual motion information. Sorry, I'm related to that. I'm happy to address some questions in the Q&A. Okay, so the challenges then. We're running out of time. Although they attempt to distance themselves from the view that Bayesian models provide mechanistic explanations, to the extent that a given model successfully constrains the search space for possible mechanisms, it will convey at least some mechanistic information and therefore qualifies a partial or incomplete mechanistic explanation. So the question is, can they have their cake and eat it too? And I think the short answer is no. And it's in virtue of the fact that incomplete or partial representations of mechanisms that characterize some but not all parts do count as incomplete mechanistic explanations. I think that's really just the basic point that I want to make, is that mechanism sketches, even though they're sketches, they're incomplete representations of the underlying mechanism, will be endowed with some explanatory power to the extent that they describe those parts, activities, and organizational features. And I think they're appropriately described as incomplete mechanistic explanations. And so that's one part of it, is sort of that mechanism sketches, even if there are gaps in the model, the representation's incomplete, they're still endowed with some degree of explanatory power. The second thing is, I think it's worth thinking a little bit more about this idea of mechanistic constraints. So a constraint is just a restriction or a limitation, and in the context of of modeling, a constraint is a finding or evidence that shapes the boundaries of the space of plausible mechanisms or changes the probability distribution of that space. So some constraints exclude regions of the space that show that some set of possible mechanisms is impossible given what is known about the components of organization. On the other hand, the discovery of a new component, a new property of a component, or a new feature of the organization of a mechanism can open previously closed regions of the space of plausible mechanisms. So that's the sort of picture we're left with. And here's sort of an intuitive example. So suppose we're trying to discover something about the mechanism responsible for delivering power to a visible car. So you discover something about the maximum rate at which a set of components, say the pistons that go up and down in the cylinders, the maximum rate at which they can move up and down. This places hard temporal constraints on the rate at which the intake and the exhaust valves must be able to open and close. And so this finding rules out many possible mechanisms with valve components that open slower than is required. And that's the basic idea. And so again, to go back to circle back to Fetch-et-al, they say that Fetch-et-al provided, this is Colombo and Hartmann saying that Fetch-et-al provided an illustration of how Bayesian unification can constrain the search space for mechanisms. It should be clear that the success of the model and unifying phenomena does not imply any particular mechanism of information integration. And so we can agree with that, but that does not imply, that does not mean that it doesn't imply any broad class of mechanism of information integration. So it provides evidence that rules in some classes of possible mechanism, for example, some probabilistic mechanisms that integrate visual and vestibular information using reliability-based rings, and excludes others in a meaningful way. So for example, a mechanism that integrates by simply averaging these two cues without regard to the reliability. And so they're finding that the model neural weights are capable of changing very rapidly, both across and within trials, is inconsistent with relatively slow mechanisms, such as synaptic weight changes. So basically they're showing this sort of this facultative change in these neurons on a trial-by-trial basis, which is too fast for synaptic weight changes to occur. And so it's not consistent with that, a whole broad class of mechanisms that have to do with synaptic weight changes, different kinds of plasticity mechanisms. And it's consistent with a fast network mechanism such as localization. And so here's sort of a picture that I've been working with. It's pretty clumsy. But it's sort of think you start with this space of all possible mechanisms, sort of unconstrained. We don't really know what the boundaries of this space are. And then you add in some findings, so like reliability-dependent Q weighting during multisensory integration. And that can be sort of behavioral data and neural data. And then it just sort of divides out the space. And so now you're only dealing with, in virtue of having that evidence, that finding, you're only looking for potential mechanisms that reside in the Bayesian sort of portion of that space. And then you add in this other thing, which is say the time scale of the weight changes. And that allows us to further subdivide that space. Right? So now you're sort of interested in just those kinds of mechanisms that implement something like Bayesian inference that are operating at a time scale less than t. Okay. And so just to sort of summarize this then, the Fetch model conveys mechanistic information. This information is what constrains the search space of plausible mechanisms, and this information is what permits the model to qualify as a partial or incomplete mechanistic explanation. And then just really sort of to get to the point, if a model provides constraints, if a model M provides constraints, M provides evidence that rules some possible mechanisms in and some possible mechanisms out. If M provides evidence that rules some possible mechanisms in and rules some possible mechanisms out, M conveys mechanistic information. If M conveys mechanistic information, M is a minimum mechanism sketch and provides a partial and incomplete mechanistic explanation. So that's sort of the first challenge. The second challenge has to do with how these different kinds of constraints that Bayesian modeling approaches can sort of place on the search for underlying mechanisms, how it can help us to arbitrate between competing and select between competing mechanistic models. I think there's a problem here because mechanistic models can be consistent with all available behavioral data and yet be inconsistent with each other. And I think this sort of reveals a tension that there are too many degrees of freedom in the mapping between models of behavioral phenomena and neural mechanisms. And I think that it also points to the fact that there's like these background assumptions that are at play about the appropriate level at which the neural model should be specified and about where in the nervous system these things are actually implemented. So I'm not going to have time to go through this model, but this is sort of another kind of alternative model that says that Bayesian inference is implemented by populations of neurons. And so the real important point is that, so this is a picture for multisensory integration where you're integrating two different likelihood functions, each represented in the population activity, each one of these dots indicating the response of a particular neuron in a population to a stimulus, a particular stimulus. And so basically you get a distribution of responses across the entire population, and in virtue of the population being, the responses of the individual neurons being noisy, you basically get something like a likelihood function from that distribution of responses in one population. So the idea here is that you've got one population that essentially represents the likelihood function for the vestibular cues, and then another population that represents the likelihood function for the visual cues, and then those two get read out by some downstream population that basically represents the posterior. So that's the idea. But critically, this model assumes fixed neural weights at the level of the individual neurons. Essentially, each neuron has a particular kind of response. There's some noise in the response, but it's not responding in a reliability-dependent way, like the fetch sort of story. And so there's an inconsistency here between these two different models. And I think the issue, so Colombo and Hartmann don't really address this, but I think most of what they have to say about the role of Bayesian framework in confirmation selection pertains to situations where one candidate model is Bayesian and the other one's not. Not where we're sort of operating in a kind of Bayesian or probabilistic regime where the real issue is, okay, we all buy into the idea that something like Bayesian inference is being implemented here, Bayesian computation is being implemented. How do we then select candidate mechanistic models? And so then can the tension be resolved? And I think one way that I think the neuroscientists are inclined to resolve this is to sort of say, well, there's a bunch of different free parameters that we can kind of play around with. One is the fact that one model is a kind of neuron level model, another one is a network or a population level model. So that's one free parameter that we can kind of tweak, so that they're really not at odds with one another. It's just we're trying to characterize two different things. But the other one I think is kind of cheap, but I think it's an available kind of response, is just to say that, look, you know, the scope of these different models is sort of limited in lots of different ways. And, you know, we might even, this fetch data is interesting, but it really maybe only applies, as far as we know, to monkey MSTD. I mean, there are human homologs of MT and MSTD, but we don't have direct neural evidence that those same reliability-dependent sort of responses are, in fact, implemented in humans. And so you could just say that the fetch model applies only to monkey MSTD, and the PPC model, this probabilistic population model, applies more widely, or at least it doesn't apply there, and so there's no conflict. Okay, so just to sort of wrap up and kind of, did we start? Okay, I'll wrap up very shortly. We're almost done. So this is just that sort of, again, that kind of inelegant picture. We've seen it up to here. So this is the idea that we start with adding in evidence about the reliability-dependent weighting, and then we add something in about the time scale. And I think this sort of picture lends, sort of the picture that we were kind of working with, and I think the field sort of tends to work with, is that, well, then you add in this additional bit of evidence, which is that there's some sort of support for this PPC model, this computational model. It's at the population level, and that it should really just subdivide that space a bit further. But that's not, in fact, what's happening. And again, this is when the responses might need to appeal to these free parameters in the different models to result in the potential inconsistency and conflict. But I think what's sort of underlying this is that there's sort of this idea that new findings or discoveries are assumed to monotonically decrease the search space of plausible mechanisms. And I think that's an overly sort of facile way to think about the role of evidence and evidence in models. So here's just a sort of picture to maybe end with and spark some discussion. I think this is sort of how we think about constraints that come from evidence, be it behavioral, be it neural. It's sort of this crossword puzzle type model where each letter that you fill in places additional constraints on what the possible solutions to this crossword puzzle are. And that's the sort of monotonically decreasing. Every letter you put in is decreasing the number of possible solutions to the puzzle. I sort of think we're kind of dealing with something more like this. So suppose you have the whole puzzle solved except for, say, the P on CHOP. And in virtue of solving that, it actually opens up an entirely new dimension of possible mechanisms that could implement the computation. I sort of think that that's maybe again, this is sort of just a very rough kind of metaphor at this stage, but I think there's something to the idea that what we're dealing with, and so those dimensions could be what level of organization is the model dealing with, what area of the brain. I think that once we come to grips with all these different factors that are in play, we'll have a better idea about the role that Bayesian models play in neuroscience. And so I just wanted to sort of end by just saying that I think this is a sort of neglected part of Carl's quote, and he actually neglects it too. He mentions it, but then he never says anything else about it. He always focuses on, like the case of LTP in the mouse, which is a really beautiful case of multi-level integration and explanation, that I think sort of underlying it is this view that there's a kind of monotonic kind of progress being made as you add new evidence from these different levels to get at that one underlying mechanism. So he said, the discovery of a new component, a new property of a component, or a new feature of the organization of the mechanism can open previously closed regions of the space of plausible mechanisms. So I think it's maybe better to think about findings or evidence providing constraints and allowances on the space of plausible mechanisms, which I think is something really interesting and something that I would love to think about further. So thank you very much.
Last time, thanks for your talk. Very interesting. Brain and cognition are biological phenomena. Biology is known for diversity. And where we find, unificatory, that's one principle in biology in evolution. One type of explanation that Tinbergen proposed. So, at its most general, right, you could appeal to William Hamilton and say, all these organisms you see on diversity of life there, they are inclusive fitness maximizing machines. So you can say the brain is an inclusive fitness maximizing. You can say something that general, inclusive fitness maximizing machine that deals with information. Right? Perhaps in a way more general or more basic than free energy. Anything else you could vary. So is that, whereas when you come to mechanism, right, then you've got all this, that's where all this diversity, you've got worms and bacteria and trees and us, all inclusive fitness maximizing machines. So is that the most fundamental element of unificatory principles that can be found in functional explanations in biological phenomena? Anyway, I imagine physics is different because it may get away with a few mechanistic principle case. That's what the standard model is.
Yeah, that's a really important point. It's something that I glossed over. So I think that first we need to be kind of clear about what the phenomena is we're trying to explain. I think in many cases we might not be sort of seeking to explain why does the system do one thing rather than another. Why does it perform one computation rather than another? Why does it generate one behavior rather than another? And I think for questions like that, one might want to appeal to some kind of optimality kind of theory that's not mechanistic or not causal, at least not obviously. And so I think that's true. However, I do think that where the rubber meets the road is that many of those kinds of questions only get off the ground to the extent that we actually know that, at least I won't speak about the biological cases, but if we say that the system is performing Bayesian computation because it's the optimal thing to do. It's the optimal way to integrate two different kinds of sensory information. Right? That's the sort of example that we were talking about throughout the talk. I think the real issue, at least to my mind, is that there seems to me to be a kind of dependency on knowing that the system does in fact perform Bayesian computation. And that sort of seems to me to be a kind of prior question that we need to answer in order to then ask the question, well, why is that the optimal solution? So I guess I sort of feel like one can take on board the idea that there are different sorts of things one might want to explain that aren't sort of obviously causal and mechanistic. But at least in the examples that I'm thinking about, there is a kind of a priority of knowing that the system does in fact implement something like Bayesian inference, and then ask that follow-up question, which is, why is that the optimal thing to do? Does that address your question, Will?
That's great. Great talk. It's a very simple question, and it's when you say an equation, part of the mechanism sketch, what's the relationship between equations and mechanism sketches? I tend to think of it as a description of the physical structure of things doing the task. Something through digestion, maybe doing perception, whatever. And you can get the same equation to describe a tuning curve can describe predator-prey relationships, as well as visual process. So if we're talking about equations and normalizations, what's the relationship between that mechanism? Part of mechanism?
Well, yes. I think that. Yes, it's a great question. Thanks. I think that for a long time, advocates of the mechanistic approach have sort of focused on kind of visual models and box scenario models and sort of models that can be kind of visually depicted. But I think increasingly, proponents of mechanism are sort of focusing on the mainstay of modeling in cognitive science and neuroscience, which is mathematical. And there, I think, to take something like the Hodgkin-Huxley model, I think there's ways to think about the early days. Again, it also sort of there's an interplay between the kind of support that I talked about, whether some of the mechanism sketch, but to the extent that that model, some of the elements in that model captured some of the activities of unknown components, it would count as a mechanistic sketch. So I think that's the sort of, and again, that's a mathematical model where there's some kind of minimal mapping between the elements in the mathematical model and something like an activity or component or the organization. In that case, it's a mapping to activity. So they basically do it on conductances. That's what they were measuring in the Hodgkin-Huxley model. But they didn't know how the conductance changes were implemented in voltage-gated ion chains.
Okay. So I really enjoyed that. I think the positive bit you've got at the end about exploring the space of allowances as opposed to just constraints, I think it certainly happens. If you think about stuff like hyperacuity, you might have thought that that's not going to be possible given some low-level sort of stuff about responses, and then it's put together in a really interesting way, and you get the phenomenon. And I wonder what the methodology is for going looking for it. So, you know, the sort of iterative constraint methodology, that's pretty easy to get your head around. You just keep constraining and see what's left. The other one, looking out for allowances, finding new allowances, you want to do it, I don't know how.
Yeah, no, okay, so thank you. That's a great point. And I guess maybe I wasn't sort of clear about what work I see that doing. And I think there's kind of maybe a normative and a descriptive component. And I think that's maybe my stab at kind of being descriptively accurate about the way in which data in neuroscience and cognitive science relates to models and can constrain our ways of modeling. But you're right, thinking about it as a sort of normative heuristic, like a heuristic that would be useful, I think it does seem like a non-starter.
Last question.
Okay, so let me try the question I asked Andy now on your model. Okay? So I want to come back to the standard story here is that the systems themselves learn, they kind of acquire models, right? And they seem to be making all the difference. But when you've got this as a constraint, do you also think these calls? I mean, it sounds like you want to use that as a constraint on finding out causing, but it's not. I mean, maybe you think that then you've got the computational story, the Bayesian story will come out on those. So there's consistency there if those turn out to be Bayesian computations, not just the model, right? But it could also turn out to be, I take it, that might not be the right mechanism in the end. So where does that, the power of that account come, right? So the general account was always that there was this general picture of that was the approach you have, all the causal power. But it looks like that's quite consistent with turning out that none of those things really do the actual work at the base level. Is that right?
So when you say might not be doing the work,
May not be the mechanisms. I mean, let's suppose it could be true that this becomes a useful tool for describing. Maybe the first pass was all the general excitement about this was we've got something that is a very useful way of thinking about these phenomena and pulling them together. But that is quite consistent, it seems, with the mechanisms not having any of the properties that those things have. So I'm pushing hard on that. Yeah. So I what you give us as treating them as constraints and that, so they can play that role. It turns out that it's not true that we're doing any basic computations.
Yeah, so I mean, I think there's a nice parallel with something that Bechtel and Richardson said a long time ago about the role of discovery heuristics in kind of standard mechanistic accounts. They talked about sort of simple heuristics that scientists use, like localization and decomposition, and that those were defeasible, those heuristics, right? They might lead us astray, but they're really useful. And again, this is sort of to Andy's point. And I think that it's sort of analogous that the kind of discovery heuristic that Colombo and Hartmann latch onto, I think is exactly the one that we use as a sort of first pass. Is sort of assuming that there's a kind of nice isomorphism between the behavior and the mathematical model that accommodates the behavioral data and then the neural model. Right? But that simple isomorphism is likely to not be true. So I think it's sort of like, simple mapping is the kind of analog of direct localization in like the Bechtel-Richardsons. Right away it's like you assume maybe a linear organization to the components and how they work together to produce some phenomena of interest. You assume that each component implements some separate activity, but we know those break down. But it's a starting.
And then maybe roots.
Okay,